All right, hello to all my academic Algebra 1 students. I got some good news for you today. This is your 6-4 performance packet walkthrough video, and this is the last lesson that you're going to have to learn this school year. So I'll give you a few seconds to celebrate, cheer wildly and loudly. Okay, sounds good. All right, I'm going to help you through the notes on this video today, and I gave you some help on the practice problems and applications on my notes file. So I'm not going to hit those too hard today. Really, we're just going to spend some time talking about the notes, and hopefully you can use my notes packet that I posted to help you get started on those practice problems and those applications. So let's not waste any time. Let's jump right into it. Today we are talking about exponential decay. So this goes hand in hand with the lesson that you learned last week over exponential growth. The good news here for you, there's really no new information to learn. There's one new formula to help you tell the difference between exponential decay and exponential growth and how to find the percent increase or decrease. But other than that, it's stuff that we did last section, and we're just kind of building on that. And you've heard me say that all year, so it should be no surprise. All right, so let's jump into it. Let's talk about exponential growth as opposed to linear growth. That's something that we've been looking at the last couple sections. Like, how does an exponential function differ from a linear function? And then we'll take a look at how an exponential growth function differs from an exponential decay function. Okay, so you'll recall, you can see it up at the top here, the directions are, and these are not on your packet, all right, so right here, write an exponential function that models each pattern. You might want to write that down as well. Directions are always important. All right, so we're looking at the pattern, and we see the numbers are not going up by the same amount every time. The difference in the numbers is changing. That's what indicates to us that we're dealing with an exponential function. Okay, so remember, if you have to multiply the previous number by something to get the next number, you're dealing with an exponential function. If you have to add or subtract something from the previous number to get the next number, then that's going to be a linear pattern or a linear function. Okay, so what we really have here is, if we look at the first pattern here, 12, 24, 48, 96. We know to get from 12 to 24, we'd have to multiply that by 2. Of course, we could also add 12, but you can see in the next step, adding 12 is not going to work anymore because we go from 24 to 48. So 24 times 2 is 48. 48 times 2 is 96. So that's the pattern that's going on here. This is how we write the function. Okay, so just a little refresher from last week. Okay, so the initial value, let me get my lightsaber out here. The initial value here, this 12, that's where the pattern starts. So that number out in front that's multiplying, that A value, that is always what the first value in the pattern is, or basically what do you get when you put a 0 in for x, okay? Because remember, anything raised to the 0 power is 1. So when you put a 0 in for x, this term always is equal to 1. And then when you multiply 1 times whatever this number is out there, you get that number. So that's why the A value is always our first value when x is 0. All right, so this function is obviously, we can tell it's getting bigger every time. If you look at the pattern, we go from 12 to 24, 48, 96. Those numbers are getting larger, so we call it a growth function. All right, and then look at the next pattern. We've got 12, then 6, then 3, then 1.5, then 0.75. All right, we're getting smaller every time. So what are we doing to 12 to get 6, and then what are we doing to 6 to get 3? Well, in this one, we could say we're dividing by 2, but I think it makes more sense to think of it as multiplying by a fraction. So we're really multiplying by 1/2. Remember, dividing by 2, multiplying by 1/2, they're the same process. So this is going to help illuminate what the difference between exponential growth and exponential decay are. You can see so we write the function the exact same way that we wrote the first one. All right, so we put the initial value here, which is 12, that's the starting value, and then the growth factor, what you multiply each term by, goes inside parentheses here. So a 1/2 goes inside parentheses. So you can see the only difference between these two functions is that growth factor, that b value. Okay, we'll talk about it again here. This is something that we've already taken down, but we'll talk about it a little bit more in depth so that you understand it. All right. But basically what the difference here is, if you have a number that's less than 1 as your growth factor, that function is going to decay or shrink. It's going to get smaller. And if you have a growth factor that's larger than 1, the function is going to get bigger. Okay, and what happens if it's 1? Well, you can see that right here. So let's take a look at our exponential decay. And remember, look, it's the same as exponential growth because we use the same formula. It's just all about this growth factor here. Okay, the initial value does not tell us anything about whether it's exponential growth or decay. We always look inside the parentheses here for this b value. Okay, so this is what you need to know right here. When b is greater than 1, that function is going to grow. It's going to get bigger, just like this one did. Okay, we multiplied by 2 every time. And here, this expression means if b is between 0 and 1. Okay, so a little bit, just a sidebar over here. If b is negative or b is less than 0, like this, like negative 2 raised to the x, it does not form a exponential function because the signs keep changing. Okay, so and we can't have that. So like we would keep going back and forth between negative and positive, negative and positive. It would not create a smooth curve. Okay, you really don't need to know about this, but those of you who want to understand why b can't be a negative number, it's right here for you. These numbers are not going to create one smooth curve on the graph. Okay, and if it's not a smooth curve, then chances are it is not a function, and it's definitely not an exponential function. So getting back over here, this is it. We just have two parts. Remember, x and y are our variables. Those are always going to be in the function. Okay, so 1 is basically the centerpiece of an exponential function. It is the linchpin. It's where we start. I keep talking about if b is greater than 1, it grows. If b is less than 1, it decays. What happens if b is exactly 1? Well, if you think about it, if we take 1 and raise it to any power, we still get 1, because it would be 1 times 1 times, like 1 to the third power is 1 times 1 times 1. That's still going to be 1. So if b is exactly 1, then this is not an exponential function. We would have just whatever. This term would always be a 1 no matter what the variable is. So you have 1 times a, which is just y equals a. This is a horizontal line. So when b is 1, a horizontal line means the function is flat. It does not grow, it does not decay, it stays exactly the same. So that's why it's the center of an exponential function. Anything larger than 1, the function is going to curve up like this. It's going to, okay, maybe it would help if I actually like drew it for you. Okay, but so if b is greater than 1, the graph will look like this. Okay, it'll go uphill like that. If b is less than 1, it'll go down like that. And if b is exactly 1, it'll just be a flat straight line. Okay, so that's basically the three things that can happen with your b values. And remember, b cannot be 0. Okay, so pretty easy to tell the difference between exponential growth and decay. So let's do a couple here, and then I'll do 1 and 2 with you, and you can pause the video and try and see if you can figure out the answer to 3 and 4. Okay, it's pretty easy, so just hang with me there. Okay, so our first function is f of x equals 2 times 3/5 to the x. So basically, remember, if we're trying to determine if it's growth or decay, this initial value, this 2 here, it doesn't make one bit of a difference. That can be literally any number. It can be negative, it can be positive, it can be a fraction, it can be a whole number, it can be anything. This is what we're looking at. Is that number less than 1 or is it greater than 1? And that's basically it, people. This is 3/5 is less than 1, so this would be a decay function. That would get smaller and smaller as x increases. Okay, on the other side of the coin here, number 2, our growth factor is 7/5. That is an improper fraction. If you go to the calculator and type in 7 divided by 5, you're going to get 1.4. 1.4 is greater than 1. So that means this is going to be a growth function. So the only difference here, and remember, they have the same starting value, that doesn't matter. They have different growth factors. This is a proper fraction, so that's going to be a decay function. This is an improper fraction, so that's going to be growth. Okay, so using what you just learned here, pause the video, do number 3 and 4. I'll come back, show you how you did. Hopefully you got that and we can move on. Okay, and let's show you the answers. So number 3 is exponential decay because its growth factor is 1/6. That's definitely less than 1, but greater than 0. Okay, right. We're always dealing with positive numbers there, so that's pretty cool. And number 4, that is a growth function because 4/3 is larger than 1. Okay, so if the fraction inside is a proper fraction, okay, so that means the numerator is smaller than the denominator, that's going to be a decay function. And if it's an improper fraction, you're going to have a growth function on your hands. Of course, it's a lot easier to tell when we're dealing with decimals and whole numbers if the number is larger or smaller than 1, but you can also tell it with fractions. All right, awesome. Moving on to the next section, okay? So sketch the graph by filling out a T-chart. Find at least 3 points, all right? Again, I'll do 5 with you. You can get your calculator out, try number 6, pause the video, and see how you did. Okay, number 5. So remember, when you're doing this, and I picked -1 down here, just to show you that you can use negative numbers for x, and certainly if you're using your calculator, it's no harder than doing any of this other work, but you want to pick values that are easy to use for x. You definitely want to pick whole numbers because you don't want to be putting fractions or decimals up in the exponent here. That's going to make things messy. And we are just, maybe all these points won't fit on our coordinate plane, but we're going to graph what we can. You can change up the scale on your graph if you want to fit those points. It's up to you, but you do need to know how to write a scale for a y-axis to fit all your points on the plane. So let's take a look at how we evaluate this. Okay, so I have all of them worked out over here on the left side. If we put a 0 in for x, then 1/3 to the 0 power is 1. 1 times 15 is 15. So we start, as always, when x is 0, your function is going to be equal to that a value, that number out in front of the parentheses. Okay, well, what happens when x is 1? Now we're multiplying 15 by 1/3, which is going to decrease the amount of the function. Okay, so 15 times 1/3 is 5. In other words, you're really just doing 15 divided by 3. All right, so and then the rest of the values you work out the same way. I want you to use your calculator every single time. You can type it in just like this with parentheses, with hit the division to get the fraction bar, and the caret button, remember it looks like an arrow pointing up, that will allow you to put an exponent in after the parentheses. So just make sure you know how to use a calculator. If you don't, you know how to get a hold of me. All right, so let's take a look at the graph. All right, so this is what it should look like. I'm going to zoom in here real quick. Woo! Sorry if I made you nauseous. All right, so yeah, you can see our first point. Remember, when you fill out a table, you're creating ordered pairs that you can put on the graph. So we have 5 points that we can fit on the graph here. It looks like I did this last one here. When x is -1, remember, to get a fraction, or to get rid of a negative exponent, you move the numerator to the denominator, and you move the denominator to the numerator. So 1/3 to the -1 power is actually a 3. So when x is negative, you get a larger number, and that makes sense because look at where this graph is going. If we go backwards, we go to -1 on the x-axis, where is it going to go? It's going to go way, 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 way up, and so it's going to be up here. You can look how steep that graph is. So that answer is going to be 45. So negative values for x also work, but we couldn't fit it on this graph because we start at 0. You can tell here. So I decided to go by 2's on my y-axis just so I could fit that 15 on there. If you just wanted to do, go by 1's, it's okay. You don't have to put this first point on there, but I really would like you to practice filling out those scales here. Okay, so anyway, I just plot these points. 0, 15 is right here, 1, 5, 2 and 1.67. Remember, I'm just trying to get that close. I know it's not going to be perfect. I'm not expecting perfection from you either. Just try and get it pretty much where you think it's supposed to go. And if you do it right, all these points should form a nice exponential curve like that. And if it's a decay function, it's always going to be getting closer to 0. But of course, it's never quite going to hit 0. So pause the video, try number 6, and I'll give you a few seconds here. Okay, pause it and do it yourself. Come back and I'll show you the answers. All right, let's take a look. Let's take the graph off here. Let's erase our marks here. And that's what you should have, okay? I'm pretty sure I rounded those correctly. All right, but guess what? If you're off, if you put 2.02 instead of 2.03, guess what? The graph is going to look pretty much the same. So don't sweat the rounding so much. Yes, you should know how to round. If you don't, it's not the end of the world. This is roughly what your graph should look like. And look, on this one, I went by ones on the y-axis. I didn't even put the numbers down here because I always go by ones on the x-axis. But we're going by ones. I didn't write all of the numbers, but you can tell every 2 lines, the numbers go up by 2. So I am going by ones here. That allows us to fit all of these points on the graph pretty perfectly. So that's pretty nice. This is so what it should look like. So hopefully you feel pretty good about that. Okay, real quick, want to talk about number 7. Again, problems like number 7 here, you are not going to be tested over, but I decided to leave it in the note-taking guide just because it's kind of cool. You might understand a little bit more about exponential functions and how to write them just by looking at it. So I'm going to go through this real quick here. In number 7, remember, if you get a table of values and they want you to create an equation that fits these points, remember, exponential functions are always about multiplying the previous value by something to get the next value, okay? So we have 4 times some b value, some growth factor, gives us 2.4, and then 2.4 times that same number will give us 1.44, and etc. So if we set up an equation that says that, okay, so 4 times b equals 2.4, if we just solve that for b, we get 0.6. If we do it for this next 2 points, 2.4 and 1.44, and solve that, we get the same b value, we get the same b value here. So I guess I didn't write it down. Huh. I wonder where that is. Okay, but anyway, doesn't matter. We can do it right now. So our initial value is 4. So our function would be y equals 4 times 0.6. There's our growth factor. That's our b value to the x. All right. See, that's not too bad. That's what the function would be that models the values in the table. Okay, 8 and 9. You do have to understand. This is a recall from last section. Okay, remember how we found the percent increase? Remember, I think this is the easiest way to think about it. That b value in there, if you think about it as 1 plus the percent increase, okay, the percentage rate, that's why we use r for that value, because it's a percentage rate, then that can help us find what the percent increase is. Okay, we did these already. This is a review, so remember, we take that 1.138, all right, that's in the, and then we set that equal to 1 plus r, and that can, and remember, obviously we're solving an equation here, so what we'd have to do to get r by itself is subtract 1 from both sides. So that's where r equals 0.138 comes from. And then remember, that's in decimal form. If we want the percentage, if we want the percent increase, we need to multiply that number by 100. So 0.138 converts to 13.8%. So what that means is this function is growing, it's increasing. You can tell that because the b value's above 1, right? Okay, so it's growing by 13.8%. Every time x goes up by 1, y goes up by 13.8%. Okay, so the second one, we have a growth factor of 2.65. So if we subtract 1 from that, we get 1.65. We multiply that by 100 and we get 165%. So every time we increase x by 1, this function is going to increase in value by 165%. All right, so that's how we do it for percent increase. We already learned that. It's just a review, but it's going to help us understand percent decrease because it works the same way, but obviously there's going to be a difference. All right, they're not the exact same. So let's take a look. All right, percent decrease. Okay, so you notice the only difference is that subtraction sign right here. Let me point it out with my laser pointer. Okay, percent increase was 1 plus r. Okay, 1 plus r right there. Percent decrease is 1 minus r, 1 minus the percent decrease. That's the only difference. So you got to be real careful that you're paying attention to which one you're going to be using depending on what kind of function you've been given. And one interesting sidebar before we move on here, you noticed in this last example, the percent increase can be greater than 100%, but the percent decrease can never be bigger than 100%, because how can you decrease something by more than 100%? If you have, if you have 8 apples, you can't decrease that amount by more than 100%, because you can only take away the 8 apples. You can't take away 9 apples from 8. That would give us a negative number for our b, and we can't have a negative number for the b. So this expression, this percent decrease, will always be less than 1, because we're taking 1, we're subtracting it. That's going to give us a b value, a growth factor that is less than 1. And remember, that's what a decay function is. It has a growth factor that is less than 1, but greater than 0. So percent decrease will always be between 0 and 100%. All right, so let's take a look at some examples. Okay, so let's jump into it here. Number 10, it says the directions say for each equation, identify the initial value and the percent increase or decrease. So first off, we need to define the initial value. That's the easy part, right? It's always that number out in front. So for number 10, the initial value is 0.5. No drama there, okay? We'll just take that value. That's where it starts. So remember, when x is 0, the function is going to have a value of 0.5 here. The next, finding the increase or decrease, the percent increase or decrease, a little bit more tricky, but the first part is really easy. You look at this number here, okay, your growth factor. If it's larger than 1, it's a growth equation. If it's smaller than 1, it's a decay function, and therefore it would be a percent decrease. But because that's 1.2, it's larger than 1, this is going to be an increase. This function is going to grow. So here's how we do it, all right? So you're going to take 1 plus r, right? Since it's an increase, since it's a growth equation, we are going to use 1 plus r. All right, we are not going to use what we just learned up here. This is only for decay functions. All right, so when the value is less than 1 but greater than 0, we're going to use this expression. But this is a growth function, so we take what's inside the parentheses, we set it equal to 1 plus r, and then of course we have to subtract 1 from both sides. That gives me r equals 0.2, and in percent form we have to multiply by 100. Okay, so if it's a growth equation, you take that number inside parentheses, you subtract 1 from it, and you multiply it by 100, and that gives you the percentage. All right, so this function is going to start at 0.5, and it's going to grow by 20% every time you increase x by 1. Okay, every time that exponent goes up. All right, number 11, a little different situation here. We have the b value is 0.7, so that is less than 1. So this is going to be a decrease. This is going to be a decay function. So you can see I circled decrease over here. Our initial value is 2. That's the easy part. The more difficult part now, since it's a decrease, we're going to use 1 minus r equals 0.7 to find that percentage, okay? And this one's a little less intuitive. With growth functions, you can kind of just see what it's going to be. It's going to be 1 plus 20%, 1 plus 0.2. This one's not so easy to see, all right? So here's how we do it. And because there's this one extra step that we got to worry about. When we subtract 1 from both sides, we get, 0.7 minus 1 is negative 0.3, but we also have a negative r here because of the minus sign. So we have to divide both sides by a negative 1 to get r by itself. And that changes that negative value back into a positive, which is exactly what we want. So basically we're saying if r is 0.3 in percentage form, that's 30%. So we're basically saying this function is going to decrease by 30%, okay? And how can we double check and make sure that's right? Well, remember, this number is 1 minus 0.3. 0.7 is 1 minus 0.3, and that's where the 0.3 comes from. So 1 minus 30% or 0.3 gives us 0.7. So even though they don't look similar like these two do, like 1.2 is 20%, it's 20% above 1. This is 30% below 1. So that's how we do those problems. All right, Pause the video, see if you can do 12 and 13 the same way I just did 10 and 11. You can already see my circles there, but that should just get you going in the right direction. All right, pause the video. I'll show you the answers here in a sec. We'll see how you did. Go. All right. So number 12, initial value is 4. Just get it from that A value there. This is a decrease. This is a percent decrease. So we take basically 1 minus R equals the number inside the parentheses. We use 1 minus R because it's a decay function. And then we get negative R equals negative 0.975. We divide both sides by negative 1 to make them both positive. R equals 0.975. And then we multiply that by 100 to get the percentage. Always include a percentage with your answer if you're writing it in percent form. All right, so this has an initial value 4 and will decrease by 97.5%. This number is very, very close to 0, so it's going to decrease like so fast. It's going to this is almost 100%. You can tell, so it's going to decrease very, very quickly. We're basically taking away almost the whole thing every time we increase x by 1. So this is going to be like a crazy curve that's going to go straight down pretty much and then go sideways. So number 13, on the other side of the coin, we have a very large number. It's very far away from 1. So when we do 1 plus R, this is a percent increase because this number is greater than 1. So we take 1 plus R equals 2.805. We subtract the 1. And yes, we are going to get a percentage that is greater than 100. But remember, with increases, with growth functions, that is possible. With decay functions, it's not possible to get a percent that's higher than 100. Okay, because that would end up making this a negative number. And remember, B cannot be negative. Okay, we are almost done. All right, we're at about 26 minutes here. That's not too bad because we did have quite a few notes to take on this today. So let's finish up strong. If you can do these story problems and you can write an exponential function based on what I give you, you're going to be in great shape. So let's try these 3 together. I'll do 14 and 15. I'll walk you through it, and then you can try 16 on your own. So let's take a look. Mr. Schaub's yard is getting overrun with weeds. Ain't that the truth? The first year he bought his home, there was 1,800 square feet of grass G. Okay, now that's important. That G there, they're defining variables for you. So if they do that, if a problem does that, you need to use those variables in the problem. Okay, so instead of y and x, we're going to use function notation here. It's going to be, t is going to be our independent variable. Okay, the time that passes is always the independent variable. By that I mean the x variable. Okay, it's just a t here instead of an x, but remember, we can use any letters we want. It is decreasing by 28.1% per year t. So t is our independent variable. G of t in function notation would be our dependent variable. That would be our y variable, so to speak. All right, so let's take a look. Did they give us a percentage? They sure did. It is decreasing, so we do have to remember that, but the R value is 28.1, which in decimal form would be 0.281, okay? And then we have to ask ourselves, so that's one piece that we need. And if we look at the formula one more time, that's exactly, remember, this is really what we're dealing with here. Y equals A to the 1 minus R over X, okay? So getting back to it. All right, we have a starting value. They did give us that information. The starting value is 1,800 square feet of grass. So that's where the amount of grass starts. It's decreasing by 28% every year. So this is what our function is going to look like. All we have to do, take this starting value, plug it in for A, take the percentage in decimal form and plug it in for R. And then, of course, instead of using Y and X, we're going to use T and G of T. That's function notation. All right, we have talked about that many times this year, so hopefully you're feeling pretty comfortable with that. But now all we have to do is simplify that expression. The only thing we need to do is subtract these numbers here. That other than that, there's really nothing else we can do to simplify it. So this is our function, and that's all. The question doesn't ask us to do anything with that function. The next one will, and some of the problems on your practice problem and your applications will ask you to use that function plug in a value for t and figure out, maybe how much grass he has left after 5 years or after 8 years, whatever it might be. All right, so let's take a look at number 15, and you can see in 15, let's read it together. All right, the value of a new car purchased for $20,000 decreases by 10% per year t. Okay, so we got the value is V, capital V. The years is t, the number of years. Write an exponential decay model for the value of the car. Then this is the additional part that we didn't have to do in number 14. Use the model to estimate the value after 4 years. Okay, so that's the whole reason we're making these models, is so we can predict the future. It's pretty cool. So let's see. Did they give us a percentage? Yeah, they sure did. They gave us 10%. So we are going to use 10% for the R value, the percent decrease, and in decimal form that is 0.1. What's the starting value of the car? That is $20,000. So our A value is going to be 20,000. So we just go ahead and plug that in. Okay. And then we do the math. There 1 minus 0.1 is 0.9. Okay. So now we take, so I'm going to get my pen out. Okay, so now we take that function, V of t equals 20,000 times 0.9, and they want to find the value after 4 years. So that means t equals 4. So we are going to raise this to the 4th power. All right, so crunch the numbers on the calculator. What do we come up with? Okay, remember, you got to do the exponent first. All right, this is probably the most common mistake that I see. Okay, if we do 20,000. So what I got on the calculator was I got 0.6561. Okay, that is a number that is less than 1. So when we multiply that, we're going to get a smaller value. And what I get is the V of 4 is equal to $13,122. So that would be the value of the car after 4 years. And that's why function notation is so cool, because it reminds you what you put in for t here. All right, so so V represents the value of the car, t represents time. So value after 4 years is $13,122. So try 16 on your own, write the function, and then use that function to model, to estimate the value of the motorcycle after 5 years. All right, ready? Pause the video, try it yourself, and ready, go. Yeah, I'm just kidding. Okay, I'm not going to give you the Jeopardy theme song. We're so close to being finished. Let's just finish it up. Okay, so number 16, your R value should have been 0.157. It is a decrease, so we're going to subtract that from 1 inside the parentheses. Our starting value is 11,000. So there's our function, and if we take that function, plug in a 5 for t, all right, after 5 years, that's a value for t, all right, t equals 5. All right, so V of 5 equals 11,000 times 0.843 to the 5th power. When I do that, we get this number right here. All right, so the value of the motorcycle after 5 years is only $4,683. So that thing is losing value very quickly, like most cars and automobiles do. After, matter of fact, you're going to lose about half of the value for a brand new car in only 2 years. So it's not really fair. It's not really cool, but that's the way of the world. All right. So that is it for your video notes. Like I said, if we scroll down here, okay, I did some of these problems for you. That should give you all the information you need to do the rest of them on your own. So I'm not going to talk about these too much. Definitely come to the Zoom session if you're having trouble with these. We can go through as many of these problems as you want. I'm not shy about helping you out with those, but the purpose is to try and figure this out on your own. So please don't just rely on me to do everything for you. Take some control of your learning. Make sure you understand this. Anything you don't, I'd be happy to fill in the gaps. But you guys are doing such an awesome job. Just want you to keep it up. Like I said, this is your very last lesson, so enjoy it. I'm going to wrap it up now. I miss y'all. Have a great week, and I'll talk to you soon. Later.